Hello everyone, I'm Daichi Mukurochi from Nagoya University. Today I'll talk about sparse iterative solvers using high-precision arithmetic with quasi multiple algorithms. High-precision arithmetic is useful for accurate numerical computation. However, most processors do not have hardware support. So we can use a software-based method, multiple arithmetic. This method uses floating point operations to combine multiple values. For example, double-word arithmetic (DW) combines two FP64 values to get about 106-bit multi precision. Similarly, we have triple-word and quadruple-word. Recently, new variants called quasi-multi-word algorithms were proposed. There are 2DW, 2TW, and 2QW. These quasi variants are faster, but they allow some accuracy loss compared to the standard version. In sparse iterative solvers, high-precision arithmetic is used for some reasons. First, we can obtain more accurate solutions. Second, we can improve convergence by reducing rounding errors. Third, we may get faster computation, and this can be an alternative to preconditioners that are not suitable for parallel execution. The key point is about faster computation. If the reduction in iterative count is greater than the increase in execution time, we can get speed. Previous studies showed that this is possible with DW arithmetic. Also, sparse solvers are memory bound, so the overhead of high-precision arithmetic may be hidden. This means we can get accurate solution without significant cost. So our question is, how effective are quasi-multi-word algorithms in sparse iterative solvers? These quasi-algorithms have been evaluated for dense direct methods, but not for sparse iterative solvers. There is a trade-off between error accumulation and performance in iterative calculations. In this study, we investigate QDW and QTW algorithms in conjugated gradient solvers. We evaluate three things: convergence, accuracy, and execution time. We compare them with FP64, DW, and TW implementations. Before explaining multi-word algorithms, let me introduce error-free transformations. These algorithms decompose floating point operation into a result and its rounding error. The algorithms are shown here. We will use these as building blocks for multiple arithmetic. Here, the addition and multiplication algorithms for DW and QDW are arithmetic. In DW, we represent a value as two parts, A1 and A2. The final step, called quick-to-sum, is normalization. This ensures that there is no bit range overlap between A1 and A2. And QDW arithmetic omits this normalization step. Similarly, here are the algorithms for QTW arithmetic. In TW arithmetic, we use three values, A1, A2, and A3. Standard TW algorithms are very expensive, and they have branches. It is a problem for SIMD vectorization. On the other hand, QTW arithmetic is much simpler, and QTW has no branches, so it is SIMD friendly. This is a big advantage. VEC3 is a normalization algorithm for QTW. It reduces bit overlap. We also use mixed precision operations when the input program is given in FP64, but we compute in higher precision internally. This reduces the cost compared to full multi-word operations. Quasi algorithms omit normalization. This causes accuracy degradation. When operations are repeatedly performed, bit overlap is increased. Actually, we found that iterative solvers do not converge without normalization. So we insert periodic normalization in CG solvers in this study. We apply normalization to the residual vector at each iteration. The overhead is minimal because SPMV dominates the total execution time. Here is the CG method and our implementation. The matrix A and vector B are stored in FE64. The solution vector X and the internal vectors use multi-word format. At line 8, after AXP that updates the residual vector, we apply normalization. We use CSR format for the sparse matrix storage, and we use OpenMP with SIMD vectorization, AVX2 or AVX512. We use this environment for experiment. For the test problems, we generate linear systems with a non-exact solution, which is a vector of all ones. This allows us to evaluate accuracy using the relative error norm. We set the initial vector to 0, and we use 3 different tolerance values. We use 8 matrices from the suite sparse matrix question. These matrices were selected to highlight iteration count reduction with high precision arithmetic. We use these matrices. First, the performance of SPMV. This figure shows the memory throughput in gigabyte per second. FP64, DW with SIMD, and QDW are compute memory bound, so they have a similar throughput. DW without SIMD and QTW are generally memory bound, but have some overhead. But TW is compute bound because branches hinder vectorization, as well as many instruction counts. And often, AVX2 gives the best performance. So we use AVX2 for the remaining experiments. This is the performance of dot product. Except TW, the throughput converges to about 90 gigabytes per second. Here we show the relative execution time for 100 iterations of CG method compared to FE64. SPMV dominates the total execution time. The overhead versus FE64 is DW is about 2.1 times, QDW is 1.3 times, but TW is up to 67 times slower. QTW is only 2.4 times slower. This shows that QTW is much more practical than TW. These figures show the convergence histories. The solid lines show relative error. Dash dotted lines show true relative residual, and dotted lines show relative residual. We can see that higher precision arithmetic reaches higher accuracy. Quasi algorithms are slightly inferior to non-quasi versions, but the difference is small. The other matrices have a similar trend. This table shows execution time, iteration count, and relative error norm for tolerance 10 to the minus 16. The main findings are: first, high precision arithmetic reduces iteration count. Second, QDW is often fastest. Third, QTW achieves TW level accuracy at a lower cost than TW. Here are results for tolerance 10 to the minus 24. We see a similar trend. And here are results for tolerance 10 to the minus 32. QDW is often fastest, and QTW achieves high accuracy at reasonable cost. This slide shows what happens without normalization. Without normalization, QDW and QTW fail to converge. So normalization is essential for quasi algorithms in iterative solvers. Let me conclude. We evaluated the effectiveness of QDW and QTW arithmetic quasi algorithms. We found that QTW significantly reduces execution time compared to TW because it is SIMD friendly and fewer instruction counts. QTW achieves accuracy comparable to TW at a cost similar to DW and QTW. So QTW is a good alternative to DW in sparse iterative solvers. Thank you for your attention.